How does first-order logic work? What does it do? Well, like propositional logic, we start with a model. In propositional logic, a model was a value for each propositional symbol. So we might say that the symbol P was true and the symbol Q was false. And that would be a model that corresponds to what's going on in a possible world. In first-order logic, the models are more complex. We start off with a set of objects. Here, I've shown 4 objects, these 4 tiles, but we could have more objects than that. We could say, for example, that the numbers 1, 2, and 3 were also objects in our model. So we have a set of objects. We can also have a set of constants that refer to those objects. So I could use the constant names A, B, C, D, 1, 2, 3. But I don't have to have a one-to-one correspondence between constants and objects. I could have 2 different constant names that refer to the same object. So I could also have, say, the name C that refers to this object. Or I could have some of the objects that don't have any names at all. But I've got a set of constants, and I also have a set of functions. And a function is defined as a mapping from objects to objects. And so, for example, I might have the number of function that maps from a tile to the number on that tile. And that function then would be defined by the mapping from A to 1, and B to 3, and C to 3, and D to 2. And I could have other functions as well. And in addition to functions, I can have relations. So, for example, I could have the above relation, and I could say, in this model of the world, the above relation is a set of tuples. Say A is above B, and C is above D. So that was a binary relation holding between 2 objects. Say one block is above another block. We can have other types of relations. For example, here's a unary relation, vowel. And if we want to say the relation vowel is true only of the object that we call A, then that's a set of tuples of length 1 that contains just A. We can even have relations over no objects. So say we wanted to have the relation rainy, which doesn't refer to any objects at all, which just refers to the current situation. Then, since it's not rainy today, we represent that as the empty set. There's no tuples corresponding to that relation. Or, if it was rainy, we could say that it's represented by a singleton set, and since there's the arity of rainy is 0, there'd be 0 elements in each one of those tuples. So that's what a model in first-order logic looks like. Now let's talk about the syntax of first-order logic. And like in propositional logic, we have sentences which describe facts that are true or false. But unlike propositional logic, we also have terms which describe objects. Now, the atomic sentences are predicates corresponding to relations. So we can say vowel of A is an atomic sentence, or above A, B. And we also have a distinguished relation, the equality relation. We can say 2 equals 2. And the equality relation is always in every model. And sentences can be combined with all the operators from propositional logic. So that's and, or, not, implies, equivalent, and parentheses. Now, terms which refer to objects can be constants, like a, b, and 2. It can be variables. We normally use lowercase, like x and y. And they can be functions, like number of a, which is just another name or another expression that refers to the same object as 1, at least in the model that we showed previously. And then there's one more type of complex sentence, besides the sentences we get by combining operators, that makes first-order logic unique, and these are the quantifiers. And there are two quantifiers. For all, which we write with an upside-down a, followed by a variable that it introduces, and there exists, which we write with an upside-down e, followed by the variable that it introduces. So, for example, we could say, for all x, if x is a vowel, then the number of x is equal to 1. And that's a valid sentence in first-order logic. Or we could say, there exists an x such that the number of x is equal to 2. And this is saying that there's some object in the domain to which the number of function applies and has a value of 2, but we're not saying what that object is. Now, another note is that sometimes as an abbreviation, we'll omit the quantifier, and when we do that, you can just assume that it means for all. That's left out just as a shortcut. And I should say that these forms of these sentences are typical, and you'll see these form over and over again. So typically, whenever we have a for all quantifier introduced, it tends to go with a conditional, like vowel of x implies number of x equals 1. And the reason is because we usually don't want to say something about every object in the domain, since the objects can be so different, but rather we want to say something about a particular type of object, say, in this case, vowels. And also, typically, when we have an x, or an exists any variable, that typically goes with just a form like this, and not with a conditional, because we're talking about just one object that we want to describe. Now let's go back to the two-location vacuum world and represent it in first-order logic. So first of all, we can have locations. We can call the left location A, and the right location B, and the vacuum V, and the dirt, say, D1 and D2. And we can have relations. The relation lock, which is true of any location. Vacuum, which is true of the vacuum. Dirt, which is true of dirt. And at, which is true of an object and a location. And so if we wanted to say the vacuum is at location A, we just say at VA. If we want to say there is no dirt in any location, it's a little bit more complicated. We can say for all dirt and for all locations, if D is a dirt and L is a location, then D is not at L. So that says there's no dirt in any location. Now note, if there were thousands of locations instead of just 2, this sentence would still hold. And that's really the power of first-order logic. Let's keep going and try some more examples. If I want to say the vacuum is in a location with dirt without specifying what location it's in, I can do that. I can say there exists an L and there exists a D such that D is a dirt and L is a location, and the vacuum is at the location, and the dirt is at that same location. And that's the power of first order logic. Now, one final thing. You might ask what first order means. It means that the relations are on objects, but not on relations. And that would be called higher order. In higher order logic, we could say, define the notion of a transitive relation, talking about relations itself. And so we could say, for all R, transitive of R is equivalent to, for all A, B, and C, R of A, B, and R of B, C implies R of A, C. So that would be a valid statement in higher order logic that would define the notion of a transitive relation, but this would be invalid in first order logic. Now let's get some practice in first order logic. I'm going to give you some sentences, and for each one, I want you to tell me if it is valid, that is, O is true, satisfiable, but not valid, that is, there's some models for which it is true, or unsatisfiable, meaning there are no models for which it is true. And the first sentence is, there exists an x and a y such that x equals y. Second sentence, there exists an x such that x equals x implies for all y there exists a z such that y equals z. Third sentence, for all x, p of x or not p of x. And fourth, there exists an x, p of x. The answers are, the first sentence is valid. It's always true. Why is that? Because every model has to have at least one object, and we can have both x and y refer to that same object, and so that object must be equal to itself. Second, let's see, the left-hand side of this implication has to be true. X is always equal to x. And the right-hand side says, for every y, does there exist a z such that y equals z? And we can say yes, there is. We can always choose y itself for the value of z, and then y equals y. So true implies true. That's always true. Valid. Third sentence, for all x, p of x or not p of x, and that's always true because everything has to be either in the relation for p or out of the relation for p. So that's valid. And the fourth, there exists an x, p of x. That's true for the models in which there is some x that is a member of P, but there doesn't necessarily have to be any at all. P might be an empty relation. So this is satisfiable. True in some models, but not true in all models.